So you see from the schedule now I'm going to talk a little bit more about one-dimensional modeling and use that to describe to you how the industry decides on the design of the air handling system in commercial internal combustion engines. Okay, so at the end of the last lecture I spoke about the Reynolds transport equation. It turns out that the Reynolds transport equation is key to deriving all of the balance equations. And the key fact is that it applies to any quantity that I've indicated with the little symbol G here. So we saw dm dt being the mass, the rate of change of mass in the system, which we said was 0 for our fire extinguisher bottle. But I can also use for G any quantity for which I know the conservation principle. So you'll see that I can apply it to mass conservation. And when I do that, I put G equal to 1. But I can also use it for momentum conservation and also energy conservation, because I happen to know what dmg dt is for the system for those parameters. Okay, so for a one-dimensional calculation, what I do is I discretize my domain along its length, and my volumes then become, in this equation, become little elements of length dx and cross-sectional area A. My transport equation is the same as I saw before. It says that the rate of change of G in the system is equal to the rate of change in the control volume plus the flux of matter and what it carries with it across the surfaces of that control volume. And so each of these little cells, if you like, will be elements of my control volume. Okay, so if I take a look at the case where G equals 1, I have mass conservation. My equation that's left here is equal to 0. That's the left-hand side here. And I have d dt of the integral of rho d volume, which is written here. And I've actually shown that the volume is just the area times dx. So I kept the area in my derivative term there. And then for the surface integral, I could use the divergence theorem to convert that into a volume integral. So this is basically my equation, conservation equation for mass. I make use of the fact that this equation, the integrand has to be 0 in order for the left-hand side to be 0 in general. And that gives me my conservation equation for mass. Now, you're going to see this equation later in 3D, but I'm just showing it to you here in 1D because we're discussing one-dimensional modeling in this segment. So that's my mass conservation. Now, I can apply the same quantity, same analysis to momentum conservation. And here I use the formula F equals ma, right? I look at the forces acting on my little control volume. The forces turn out to be due to pressure. There's a difference in pressure across the faces here, which gives rise to this term dp dx. And then I also have frictional forces on the walls of my little volume. And that's this term here. The frictional forces scale with the velocity squared, the diameter of the duct, and a friction factor, F. And then this term that's left over, it corresponds to the acceleration term, which has both a time-dependent term and a spatial-dependent term. So that's my momentum conservation. And in this case, my quantity G here is just V, the momentum per unit mass. All right? So that's how we derive these equations. Now, of course, for energy, I have the same kind of idea, except now I use my first law of thermodynamics again. On the left-hand side, I have my the rate of change of energy in my control volume. Which is, again, has a time-dependent term and a spatial term. And then on the right-hand side, I have my heat loss terms due to heat transfer across the boundaries of my little control volume, which I've indicated by Q dot. And then because of friction, I actually have dissipation occurring, or heating, that contributes to the energy equation in the amount of V cubed. And my friction factor. And then the final term is our work, our pressure volume work term. It takes some work to push the fluid across these surfaces, and that's where this term derives from. So those are the one-dimensional equations. There are 3 equations, and if you count up the number of unknowns, you see I need more equations. So I supply my equation of state, which relates the pressure, the density, and the temperature, and the ideal gas constant here. The caloric equations, and then for the friction factor, I have to use some kind of engineering analysis, typically involving a wall shear stress from a correlation of some sort. But when I'm done specifying that, I see I have 5 unknowns, which I'm going to call capital U. They are the density, the velocity, the internal energy, the pressure, and the temperature. And I have 5 equations, 3 partial differential equations plus these algebraic equations that relate to the variables. And I also have to specify the heat loss term. I have to use some sort of a correlation to provide an estimate of how much heat is crossing the surfaces of my control volume. So 5 equations, 5 unknowns, I'm in business. And that's what is done in solving the 1D equations. However, those engineering terms that I have to add, for example, the friction factor, they account for a lot of parameters. For instance, the flow in an actual engine has to undergo tortuous bends in the passage, flow separation effects occurring where you have a divergent part of the duct, flow separation, again, with changes in cross-sectional area and direction. And what is typically used is experimental correlations for these friction factors. And basically applying a friction factor that gives you the same amount of friction you would get from some equivalent length of pipe to the shorter pipe that you have with these losses. So the codes that you will find that are widely used in the industry are the Gamma Technologies GT Power, AVL, Boost, Ricardo Wave. And these codes are used to predict wave action in manifolds. Remember I mentioned the wave action earlier. And in fact, at high engine speeds, we saw that you can actually use the wave action to help improve breathing. The inertia of the flowing gases can cause inflow even during the compression stroke. So how's that possible? Well, here's a picture that shows an internal combustion engine. Here's your piston, here's your intake valves, and you have a certain manifolding, certain length of manifolding. Imagine that the piston moves a little bit, all right? So the density immediately above the piston decreases, and that's going to demand fresh gas from the intake system to fill that void. Well, how does the flow system get set up? Well, a signal is sent from the piston at the speed of sound all the way back to the intake system saying, I just moved my piston, please send me some more gas. Well, this signal travels at the speed of sound, which I'm estimating here is 330 meters per second. Let's say the length of the duct is 1 meter. That's a fairly long duct. It takes 3 milliseconds for that signal to travel all the way back here to say, I just moved my piston. By the way, 1 crank angle degree at 1800 RPM is 0.1 milliseconds. So this is 30 crank angle degrees that it takes. That's why at high speed we wanted those short manifolds with the Mercedes system, right? You want to be able to respond. So basically the communication of changes that are going on here are due to waves or sound waves in the system that control the flow that's going to be experienced through the intake system. And because of this delay, you can have flow being demanded even when the piston's moving up, because this guy here doesn't know that the piston is moving up until 3 milliseconds later. So that's one of the things that's included in the calculations when one uses these 1D codes. For example, here's a Ricardo Wave layout for a 4-cylinder engine. Here's your intake manifold, each of these supplying one of the cylinders. Each of these little segments here corresponds to a section of pipe, which may have a length, a diameter. It might be a tapered pipe or a diverging pipe, may have bends. All of these things are specified by the user of the code. Here's a compressor, and this goes back all the way to the atmospheric inlet position. And then you have a similar set of ducts and so on the exhaust side, and presumably you have a turbocharger. So these codes are widely used and are actually extremely useful, as we'll see later, for estimating some parameters of an engine system. I should just mention that they also help you to determine how much residual gas might be left in the combustion chamber from the previous cycle because of this emptying and filling process that's simulated in the code. They allow you also to track variable valve actuation technologies, to control valve timing. You can use that to control the compression ratio through Atkinson cycle, for example, for early or late intake valve closure. Exhaust reinduction to control in-cylinder pressures. All of this stuff can be simulated using these 1D codes very accurately and helpful in the design of the overall engine system. Just a little bit about the numerical solution method. So here's that duct that we said we broke up into little lengths of dx. And in each of these little control volumes, we have our our dependent variables, capital U, which will be the density, the velocity, the energy, the pressure, the temperature. Each of these spatial intervals is indicated by the subscript I, and the time variation is indicated by the superscript n. So at time t equals 0, n is 0 here, and we presumably have initial conditions, and then we let the system develop. The derivatives in the equations that I showed you earlier are approximated as finite differences. So for example, the spatial derivative would just be the quantity of whatever it is, pressure, temperature, so on, at a particular location minus the value at the next location divided by the distance between them. And similarly for the time variation, here we would indicate that by solving for quantities at the new time level, un plus 1, given the quantities at time level n for each of the I values, each of the location indices. So that's basically how these techniques work. There are, however, numerical parameters that you have to worry about, and we'll see the origin of them on the next slide, but basically you can't just take an arbitrarily large time step. There are certain restrictions that involve the velocity of the flow and also the sound speed. But anyway, just to show you how, and in this case in Ricardo wave, here's a piece of duct. You specify the duct diameter, you specify the duct length, and parameters associated with the duct, friction, and so on. And you do this for each of the elements in your model as you set it up. Very powerful modeling tool. So why are there these time step restrictions? It's easiest to understand if you look at what's called the method of characteristics. So here's a plot of distance along the duct, and I'm tracking a particle as it moves along the duct from, say, the inlet to the exhaust as a function of time. So the particle is moving at velocity v. What is making it move? Well, it's moving because there's a pressure gradient in the duct that's pushing the particle. This is in layman's terms, if you like, pushing the particle down the duct. Well, how does the flow develop? Basically, we have high pressure at this end and low pressure at this end. We may have changes in cross-sectional area along the flow path. All of that has to get communicated to this particle in order for it to determine how it moves. And so these, what happens is a signal is sent from every point in the domain saying what the pressure is, what the velocity is, what the density is at that location. And similarly, you see there's something that's going in the opposite direction from the downstream location. These are called the right running and left running characteristic lines. And they have slopes that are the velocity plus the sound speed for the right running wave, and the velocity minus the sound speed for the left running wave. And where the two intersect, there's enough information to provide all of the solution variables that are needed to determine the particle path, which is the distance that it moves in a given time, namely the velocity of the particle. You'll notice that the parameters that are of interest here are the velocity and the sound speed. The ratio of those two is the Mach number, all right? And it's kind of interesting to note here, just something to point out, that if the velocity is equal to the sound speed, in other words, the Mach number is 1, the left-running wave here becomes a vertical line. No information is sent back upstream when the Mach number reaches 1. So that's kind of an interesting parameter that we'll see later as well. So why is there a time step restriction? Well, here's my delta x, my distance along the duct that I've discretized the domain. And as you can see, if I have a signal that traverses more than that distance, I will not be providing the correct amount of information to the fluid inside that control volume. So that restricts the amount of that I can advance time, the amount of delta t that I can choose. So delta t then turns out to be the minimum of delta x divided by the velocity, the absolute value of the velocity plus the sound speed. It's called the Courant-Levy-Friedrichs condition. Courant-Friedrich-Levy condition, CFL condition. So that's just something to bear in mind, and it's very interesting to understand the physics behind that, is that sound waves are propagating in our compressible flow that are basically informing each fluid particle about the conditions upstream and downstream of their location. If you look at the method of characteristics, you can actually go further and show that along the right-running characteristic, changes in pressure are related to changes in velocity through a source term F here, which is a function of the heat transfer, the friction factor, and the area change. And similarly, along the left-running characteristic, there's an equation. And along the particle path, there's another equation that relates density and pressure changes. So how do you use these equations to solve the flow problem? Let's say here's my duct, and I'm interested in finding out the conditions at station 4 here, given that I know the whole flow field, all the parameters at station n. Well, I know that information will be arriving at station 4 along a right-running characteristic line that originates at the point R, and information from the left-running characteristic will arrive at the point 4 from the point L. I will know the flow field at points L and R by interpolating between 1 and 2, or 2 and 3, to find the density, the velocity and pressure at those locations. And therefore, I can solve these equations for the conditions at station 4. Here are the equations. These are discrete versions of the equations. And you basically have 3 equations to solve for the variables density, velocity, and pressure. Actually, it turns out these equations are even simpler if we have an isentropic flow. For an isentropic flow, ds is 0. You can show that, therefore, this term on the right-hand side is 0, h is 0. And then you find that dp d rho is just c squared, which we happen to know, if you remember, change in pressure is related to change in density, the isentropic change in pressure and density giving you the sound speed squared. So in that case, these right-hand sides, it turns out all these right-hand sides are 0, and you can solve these 3 equations very simply to advance to the next time level. So the method of characteristics is actually a very powerful tool, not only for understanding how a flow is set up, but also for actually solving the flow field. And it's used by some codes. The other thing that it's useful for is to understand the question that I mentioned in the last lecture, which is, why is the pressure uniform in a combustion chamber? Well, here we have a picture that shows that XT diagram. So here's the head of the engine, here's the piston location and time over here. So the piston's moving along this path, all right? Every time the piston moves a little bit, a wave, a left-running wave, is sent out saying the piston velocity is whatever it is at that moment. This wave reaches the head, all right, and it finds itself at a 0 velocity boundary. So it has to reflect back and send a right-running wave saying, oops, no, the velocity here is 0. And so during this traverse, backwards and forward, information about the movement of the piston is being transferred to the gas, which is increasing its density and pressure. And the equations are, as I've written over here. If these lines are more or less horizontal, what that means is that the speed of sound is much larger than the piston velocity. And that means that everything is equilibrated extremely quickly across the domain. And you can show from order of magnitude analysis then, pressure changes being related to velocity changes and density changes being related to velocity changes, that if the velocity changes are very small compared to the speed of sound, the density and the pressure everywhere in this combustion chamber is uniform. So that's great if you're an experimentalist, because you can put your pressure transducer anywhere you like in the combustion chamber and measure the pressure, and you know it's the pressure. All right? Now that breaks down if the flow velocities become sonic, as you might experience in some abnormal combustion regimes like with detonations. And we'll talk about that. But that, of course, means that you're going to have your pressure transducer be aware of where it's located and interpret its measurement correspondingly. This is also just a quick review of steady compressible flow. Remember that the flow in an engine is compressible, right? We have a gas. So we also are going to use these equations when we study turbochargers. So we mentioned the Gibbs equation before for calculating entropy. If I assume that I have an isentropic process, which is the first simplification that we're going to introduce, that means a flow without heat transfer, and it's a reversible process. There are no irreversibilities like friction. Then my Gibbs equation allows me to relate enthalpy and pressure changes. The energy equation I can use to get the enthalpy. And if I put these all together, I get what's called the Euler equation, which relates pressure changes to velocity changes in a flow. We know that from the continuity equation, the density times the area times the velocity must be a constant, right? So we can write that in differential form, as I've shown here. So now this is very useful, because what it can allow me to do is, if I know how the area changes in a duct, I can use these equations to determine how the density, the velocity, and the pressure change. So, for example, the area-velocity relations. If I have a duct where the flow everywhere in that duct is subsonic, the Mach number is less than 1, the velocity is less than the speed of sound, then what you can see from the solution of these equations, which is shown over here, Mach number is less than 1. That means if the area is decreasing, the velocity increases. Shown over here. And from the Euler equation, the pressure decreases. So this is called a subsonic nozzle, right? The area is reducing, the velocity increases, the pressure decreases. You're converting kinetic energy into potential energy into kinetic energy. On the other hand, if I have a diffuser, namely the area is increasing, so dA is greater than 0, then my equation for subsonic flow shows that the velocity decreases and the pressure increases. So I have pressure recovery. The interesting thing, though, is that if I am now dealing with a supersonic flow, so the Mach number is now greater than 1, I get completely the opposite conclusions. A converging duct is called a supersonic diffuser, because as the area change is negative, the velocity decreases and the pressure increases, and vice versa. If I look at an expanding duct or a nozzle, the area change is positive, the velocity change is positive, and the pressure change is negative. So I convert my internal energy into kinetic energy. And if you ever want to remember about that, just think of the frustration you experience when you're driving on the New Jersey Turnpike or some road where you go down from from 2 lanes to 1 lane. You find that you slow down. It's the opposite of what you should do. And that's because traffic flow behaves like a supersonic flow. Essentially, as you're converging your flow into this duct, like in our supersonic nozzle here, you slow down and you get mad, and then you come out the other end and you speed up. So that's what happens for a supersonic flow. A subsonic flow speeds up like you would expect it should do, right, through this intersection. And why is that? Well, the reason is that this guy here is sending information about his position to the guy immediately behind him. And this guy over here knows nothing about that guy back there. So he hasn't had this communication process occurring. Information along the left running characteristic, if you like, never reaches back here. It's like a supersonic flow. So that's just an interesting thing to remember. If I look at the equations for isentropic flow, I can actually use them to study nozzles. My energy equation can be shown to give you this result here. And from the isentropic flow equations, I can relate that to pressure changes through the ratio of the specific heats. And so the equations are in the boxes. So let's just look at an example. I have a reservoir at P0, that's our stagnation state. And it's connected through a nozzle, a converging nozzle, to the ambient here, which is at a certain pressure. Well, they communicate with each other through these left and right running characteristics, right? Information from the ambient spreads back to the reservoir saying, hey, my pressure is much lower than your pressure. Please send some of your flow to me, right? So if you look at this plot down here, which shows the ratio of the pressure at every point in the nozzle divided by the reservoir pressure as a function of distance along the nozzle, you'll see that if the ambient pressure is the same as the reservoir pressure, we have no flow, right? But as I lower the back pressure, the ambient pressure here, I generate a flow, and therefore, using my area velocity relations, I see a pressure drop. And if I continue that process, I keep lowering the back pressure. Eventually, I reach the point where the flow at the exit of the nozzle becomes sonic. In other words, the Mach number equals 1. And you can see that from this equation here. When m is 1, if I put 1.4 for gamma, which is a typical value of the ratio of specific heats, I get 0.528. So if the pressure in the environment is less than 0.528 of the reservoir pressure, I will have choked flow. No more flow will be supplied no matter what the back pressure. So you can see that an example of that in your intake system here. Here your piston moves down, creates a lower pressure region. That means that now you want more flow to pass your throttle plate. If for some analysis you find that the pressure downstream of the throttle plate is less than 0.528 times the supply pressure, you'll have choking. So if I look at the mass flow through my nozzle plate here for different angles of blockage or different flow areas, you'll see that my ambient pressure is 76 centimeters of mercury. If I lower the pressure P1 here to 40 or below, I will choke the flow in this region, and I'll be able to get no more flow. That means that no matter how fast I move the piston here, once the pressure below, or in the region behind the piston drops below 40 centimeters mercury, I can't get any more flow, and the flow is choked. So that's what I was referring to when we looked at Hayward's plot when we spoke about the choked flow situation. Okay, so it turns out that for turbochargers and compressors, we can actually look at the flow, compressible flow, in converging, diverging nozzles as a way of understanding those flows. And a very important formula that's used widely in analysis of turbocharging equipment is what's called Fleetness Formula. It's derived simply by looking at the mass flow rate, which is rho times area times velocity, and introducing the Mach number by dividing by the speed of sound, which is square root gamma RT, and rearranging it, putting in those equations on the previous slide for the pressure divided by the stagnation pressure and temperature divided by stagnation temperature, and then setting m equals 1. And here you have the formula. What it says is that the mass flow rate, when the Mach number is equal to 1, is determined by three parameters, really. The pressure in the reservoir, the minimum area, cross-sectional area, and the temperature in the reservoir. So here's my duct, here's my reservoir at pressure P0, here's my minimum cross-sectional area point, and of course I had a temperature here as well. Those parameters determine how much mass flow can pass through this converging, diverging nozzle. Actually, you can show these area Mach number relations and get the area, the Mach number at each point in a converging, diverging nozzle as a function of the local cross-sectional area from these equations, and you can plot them. And these plots are very useful for people who want to understand the relationship. So there's a subsonic side and a supersonic side. You can have, for the same cross-sectional area, either a supersonic flow or a subsonic flow, depending on the local pressure in the duct. So that's very useful. But for turbochargers and turbocharging equipment, Fleetness formula, which relates the mass flow to the pressure and the cross-sectional area, is used as a normalization. So here it is. What you'll see when you look at a variable geometry compressor turbine performance map, for instance, is the corrected mass flow rate, which is the mass flow rate through the turbine or turbocharging equipment that has been normalized by some reference temperature and the stagnation temperature and the pressure and some reference pressure. And it all comes from Fleetness formula. And you can think of this grouping here as being a measure of the effective flow area, our A star here. So when you look at turbocharger maps, you'll see them plotted against a corrected flow rate, mass flow rate curve. And then on this side, this axis is the total to static pressure ratio. And you can see here, if the static pressure is equal to the total pressure, I don't get any flow, right? We already saw that. But if the static pressure is 0.5 to 8 times the reservoir or total pressure, then I get choked flow. So the different curves that you see here would correspond to different speeds of flow through the device, and each one here for a different cross-sectional area passage. Okay, so this will help you understand both compressor and turbocharger maps when I show them to you. All right, what's the history behind turbocharging? Well, in 1925, a fellow by the name of Bushi patented the pulse-driven turbine, which was used to increase the amount of air inducted into an internal combustion engine. And it turned out that the increased engine power from getting more air into the combustion chamber more than offset the losses due to the increased back pressure. You need higher back pressure or pressure coming out of the engine to drive the turbine, which then compresses the inlet charge. And it turns out you get more power than you've lost due to rejecting some of the work associated with the increased back pressure. There are considerations, though, such as turbocharger lag, because you basically have to spin up this turbocharger as you change the speed of your engine. So there's a lot of design that goes on behind us. But if you look at this plot here, which basically shows the specific torque versus specific power for engines of various classes. Here's the turbo gasoline engine. Here's a turbo diesel. You can see that the trend from naturally aspirated engines is such that you can drastically increase the power. I mean, we're going from 30 to 70 kilowatt per liter here by going to a turbo from a naturally aspirated engine, and a corresponding increase in torque. So turbocharging is here to stay. If you look at examples of turbocharged engines, here's, I think this is a Volkswagen twin-charged engine. Here is your fresh air, which can pass through through the compressor and then into the engine. You can also bypass this part here and have a supercharger, a mechanical supercharger that's driven by a belt from the engine. So you can have both mechanical turbocharging and a compressor driven by the turbine. The turbine itself is driven by the exhaust flow, which is shown in red over here. So this allows tremendous control of the engine. So in cases where you might have turbo lag as a problem, you might want to use your supercharger, or if you don't have enough exhaust energy, you might use the supercharger and then phase that out when you have sufficient power from the exhaust to drive the compressor. Also, in certain kinds of engines, such as two-stroke engines, where the intake pressure is generally larger than the exhaust pressure, you need a different way to pressurize the intake, and here the crankcase can be used as a pump. Notice there's also the introduction of an intercooler here, and the idea there is you've compressed this gas, you've increased its temperature with an intercooler that's water-cooled, for example. You can now increase the density of that gas and thereby get more mass into the combustion chamber. So managing the airflow is a key component to generating high-performance engines. These are just some pictures showing some cutaway views of turbo compressors. So here's your turbine, here's your compressor. These are the rotating vanes over here. You'll notice also there's a wastegate here, which allows you to control how much of the exhaust actually goes through the turbine. Maybe you don't need all of that exhaust energy, so you can open this valve here and bypass some of the flow. So here's another example of an even more complicated arrangement. Here you have an 8-cylinder engine, like a V8. Here's your 4-cylinder bank. We have, in this case, 2 turbines using the exhaust energy to drive a low-pressure turbine and a high-pressure turbine and a low-pressure turbine, which in turn drive the low-pressure compressor and high-pressure compressors. So you have basically 4 rotating components with regulating valves and bypass valves to control just how much of the exhaust energy is used to compress the gases. Maybe at low speeds, idle, you don't need to have the high-pressure stage running or the low-pressure stage, whatever. Here you see a picture of a GT Power palette of layout for such a system. Each of the ducts here is going to have certain lengths and bends and diameters and so on, and all of that has to be fed into the model in order to model such a system. But once you have it in place, you can start looking at control strategies. When should I open this valve and close that valve and regulate the flows? Okay, so now let's just talk about the air handling devices. The compressor, usually driven by the turbine. In automotive applications, we typically use centrifugal compressors. They provide high mass flow rates and relatively low pressure ratios. So they can pressurize you up to about 3.5 atmospheres. They rotate at high angular speeds, and they're coupled to the exhaust-driven turbocharger. So here's just a picture of them. You have your impeller here. Your inlet flow is, of course, accelerated by the impeller. And then through a nozzle arrangement, you pressurize the gas, which is then used to provide the boosted pressure for the inlet. So here's just a cross-sectional view of that. Here I have my flow entering from the environment, let's say, through a converging nozzle. I then go through the impeller, right, with the rotating blades. Then I go through a diffuser section to remove the kinetic energy and convert it back to a total energy state. So air at stagnation state 0 accelerates to the inlet pressure 1. So if I look at my TS diagram here, here's my stagnation state. That's the atmosphere, right? I accelerate the flow to state P1 over here through my converging nozzle. I then, within the compressor, provide a significant amount of energy due to the rotation of the impeller. And this increases the pressure to P2, and the velocity of the flow is V2. And then I have a diffuser between states 2 and the out, which recovers the kinetic energy, producing a pressure rise to P out. So that's this guy over here. And that would be the pressure that goes into the combustion chamber. So if you want to calculate the work required to drive the compressor, would be the mass flow rate times the difference in enthalpies at the outlet stage and the inlet stage. And so if I use my equations of state and so on, the caloric equations and so on, I can relate that to the specific heat at constant pressure, the temperature at the inlet, the pressure at the outlet, the stagnation pressure at the inlet, and the ratio of the specific heats. There's a quantity here called the efficiency, the compressor efficiency, and you can identify the difference here is associated with the difference between an isentropic compressor and a real compressor. So one point is that you use the exit static pressure, that's our P out over here, and the inlet total pressure when calculating the work required by the compressor. So just a little picture of what the compressor is doing there. It's raising the temperature in the impeller passages. Okay, so when you're all said and done, if you are a designer of internal combustion engine air handling systems, you will have interest in getting a compressor map. A compressor map looks something like this. Here's your mass flow rate that's been normalized using Fleetness Formula, as we discussed earlier. And here's the pressure ratio across the compressor. And you can see there are various curves here which are associated with running the compressor at different speeds. And again, we're normalizing that against the speed of sound. That's why there's a square root t here. Remember, the speed of sound is gamma RT square root. And there's these lines that you see here, which are the compressor efficiency lines. You'd like to operate somewhere in this high compressor efficiency region. There are other lines on this plot here that are of interest, namely the choke line. You can only go to a certain mass flow rate before the system chokes at the minimum area point. So that basically truncates the compressor map at this location. And then on the left-hand side is what's called the surge line, where essentially you can have flow separation effects in the diverging sections of the design that, again, lead to losses. And you can have periodic flow, reversal, reattachment, and instability. So you have a surge phenomenon occurring in a compressor. You want to avoid that, otherwise you'll see serious damage. So that's what a compressor chart looks like. How do you choose a compressor? Well, you need to know basically the airflow demand for your particular engine. So here's your estimate of the mass flow rate at the intake. You need the volumetric efficiency, the displacement, the speed, and then the desired pressure ratio from your compressor and temperatures. So the way that you'll do that is you take a look at your engine layout. Here's your desired load, which is measured as torque here, and speed. You have a peak torque location. You'll have a rated speed location. And at each of these points here, you'll have a certain mass flow passing through the engine. And that's basically plotted here. Compressor pressure ratio needed to provide a certain mass flow rate at the peak torque and rated load points. So you'd like your compressor map to basically fall inside this region here. And in that way, you have designed the correct size compressor for your particular application. So here's a real compressor map from a GM 1.9 liter engine. Here's your pressure ratio. Here's your corrected airflow. Each of these lines here corresponds to the compressor operating at a different rotational speed. Here's your surge line, and on the right here are the choke flow lines. As you move along each of these lines here, there's also a consideration of efficiency. I showed you that there are peak efficiency locations that have to do with flow separation in the impeller and so on. And so combining the efficiency chart with the compressor map tells you where you would like to position the lines that I showed you over here, so that you ensure that you have your highest efficiency right in between these two lines, your breathing lines. Okay, so that's the compressor. Now, the compressor is driven by the turbine, and now it's basically a very similar device. Where are you getting the energy from? Well, if I go back to my PV diagram for an engine, here I compress, here I have some combustion process, here I have expansion, and now the exhaust valve opens at state 5 here. Normally, in a naturally aspirated engine, this high energy exhaust is thrown into the environment. But instead, what I'm going to do is I'm going to capture that energy and send it to my turbine. And depending on whether I want to have my device arranged with higher intake pressure than the exhaust pressure or so on, will depend on how I design my turbine and compressor system. But basically, the work required or extracted from the flow by the turbine is the mass flow rate, the difference in enthalpy across the turbine, which again I can relate to the pressure ratio across the turbine efficiency, the specific heat, constant pressure, and all of those are parameters that you would use if you were designing a system. We already know what we want from our compressor. This would help you then design the corresponding turbine. Here's what the turbine looks like. We have our corrected flow parameters, just like we had for the compressor. We have corrected speed parameters. And we'll also have a turbine map. It's very similar to the compressor map. And again, looking on a TS diagram, you can understand the processes whereby the inlet flow is accelerated, which is, of course, the exhaust flow from the engine, accelerated and used to drive the compressor. So here's matching of the compressor chart and the breathing lines that I showed you before. Here's our pressure ratio. Here's our corrected mass flow rate. You can see the surge limit here. Here we have the choked lines for different speeds of rotation of the compressor. If I look at my breathing lines, I can also look at what would be required at constant load and at constant speed of the engine itself. And I want to make sure that this map, which represents the load range and the speed range of my engine, falls squarely inside the compressor chart as I've tried to show you here. This one is not quite arranged well. I would actually want to move this up to capture more of the high efficiency part of the compressor. So how do I actually calculate in a model the exhaust and inlet, the relationship between the exhaust pressure and the inlet pressure for a given turbine arrangement? Well, we know that the turbine work and the compressor work must be equal. So if I look at it this way, my compressor goes from state 1, my atmospheric state, to the boosted inlet to my engine, state 2. The exhaust from the engine is state 3, goes across the turbine, and is exhausted to atmosphere at state 4. So if I plug in the equations I showed you before, I can relate from my turbine work and my compressor work the pressure ratio across the inlet, or the compressor, to the pressure ratio across the turbine. And the parameters you see here are shown. You have your temperature at the exit of the engine, of the exhaust, the inlet temperature, the fuel-air ratio, the turbine efficiency, the compressor efficiency, and then there's usually a mechanical efficiency thrown in here as well. Usually it's 90-something%. And then the pressure across the turbine. So this equation is used widely to estimate the boost pressure from a given exhaust pressure. Okay, so what I've tried to do in this section of the presentation is to discuss how you can use these 1D models to set up an engine system. And this is widely used in the industry. Every OEM has GT Power and Ricardo Wave experts, AVL boost experts, who design the entire layout of the intake system, the turbochargers, the compressors. And everything is done without considering the combustion chamber. And that's what we're going to talk about as we move on. But for now, all that they say is they assume that you have a certain pressure at the exit of the exhaust system that's driving the turbine, and you're going to use that to then boost the inlet. But how you're going to use that, those two bits of information, really relies on understanding what happens in the combustion chamber. So these 1D models are very useful for understanding charge preparation and engine breathing, and in fact, they're essential for understanding that. They do require calibration, like, for example, we needed friction factors, we needed heat transfer correlations in order to evaluate the system. And we had to make some assumptions about the efficiency of the turbochargers and compressors. But when all is said and done, as I pointed out in one of my slides, turbocharging increases the overall engine efficiency. It uses available energy in the exhaust and actually reduces pumping work. So this is one of the differences, for instance, between an external combustion analysis like an Otto cycle and a real engine where you're actually using some of the exhaust energy to help drive the combustion process. Here are the references that I referred to during my presentation. You're welcome to take a look at them. So we have a few minutes for questions. Yeah. Yeah, so it's very complicated, as you can see. I think I showed you one plot where we had low pressure turbine, high pressure turbine, each driving the corresponding compressors. And you have to basically decide what the flow split is and optimize it for a given road load condition, engine speed. So, there's a team of 100 engineers working at BMW or maybe more than 100 or VW or wherever, trying to design the flow system to maximize the amount of mass you can put into the combustion chamber. It's not a simple process. And of course, I can tweak it by changing the length of the passage here or the diameter of the passage, or I can remove the flow restriction so I don't have choking here. Extremely complicated. It's taken years of development to get to where we are today.
I was going to ask if you wanted to embellish a little bit on that. Where all these numerical numbers come from, the friction factors, et cetera, what the historical issues.
All of that comes from very simple experiments like, that are done in fluid mechanics labs around the world. There's a book this thick that comes out of Russia. I forgot the name of the author. That has friction factor for every kind of pipe you can think of. Pipe roughness, bends, diameter change. It's an amazing amount of information that's put into these codes in the form of tabulated data that is used in interpolations and so on. None of that would be needed if you use CFD. Right? I'm going to talk about CFD later, but CFD isn't at this level yet, where an engineer can come in, play with the parameter, and see the result immediately. CFD engineer plays with something and comes back a few days later and looks at what happened. Any other? Yeah.
So I might have missed it, but in the derivations you assume that the flow was isentropic. So in our analysis, how do we account for the irreversible energy?
Yeah, thank you. That's these guys here. Okay.
Yeah.
So there's a lot of stuff buried in that number. Losses that are turbine efficiencies, compressor efficiencies. But actually, if you look at the numbers, you can get very far by making a very simple assumption. Turbine efficiency is 0.7. Because, the other thing to remember is that in the engineering world, trends are more important than specific items in many cases. So I could change 0.7 to 0.6 and see what happens. And I'll say, oh, well, all my boost pressure changes is 0.1 bar. Oh, I can live with that. Okay.
There's two words that have stuck in my head about that issue, and they also apply to chemistry. in combustion. That is fidelity and accuracy. He can get very good fidelity with this modeling process. And the accuracy that comes from optimizing the result that comes out of this against a specific case. That's also true when you think about chemistry and combustion kinetics, where you may have 10,000 reactions and only 150 are really important to the target that you picked. What happened to the rest? There was sloppiness in the problem. You still have good high fidelity with only those 130 parameters of the accuracy. And the accuracy is coming by calibration and some set of experiments.
Yeah, that's what engineers.
That's what engineers do. But that's also why many things work. Because engineers do that.
And the other thing to remember is that, you know, at Ford or General Motors or any of these companies, at the end of the day, the model has all of these ingredients, but at the end of the day, they make a table of pressure versus something, or, you know, boost pressure versus exhaust pressure or whatever. And that's what goes into the engine ECU, that table. And it has parameters that are all just code fits from these analyses. And they tweak them, make sure that they match experiments, but it's all on the fly when you put your accelerator table, look up, happens, throttles change, valves open, close, it's all starting from these models that tabulated the results.
The reason I raised those two words was when you're thinking about doing fundamental research and fundamental science, one of the most important questions is what you're working on as to whether it's going to affect the fidelity of the prediction or it's only going to improve its accuracy. For myself, I think the more important one is the one that changes the fidelity issue, because I can always correct the accuracy issue with good engineering.
Okay, I think we need to 4:30, right?